our next speaker, who is going to be Felipe Gonzalez from UC Berkeley. And he's going to speak about non-ideal mixing effects in the warm-dense matter.
Thank you, Francois. So yes, my name is Felipe Gonzalez. I'm a postdoc at UC Berkeley. And today I want to present our work on non-ideal mixing effects in warm-dense matter. In particular, in these three materials, boron nitride, MgO, and MgSiO3. If you were present in the first talk of this session by Burkhard Militzer, you may have noticed that the code he provides relies on the ideal mixing approximation. The work that I will present here basically represents the foundations for the work that Burkhard presented. So in our work, in our group, we have experience generating equations of state of matter at extreme conditions, but one has to be really careful when temperature ionization takes place, because the innermost electron shells can become ionized. It excites the inner shell electrons, and that has to be taken into account properly in order to generate an accurate equation of state that can describe the material as these conditions. So we expect this to happen in the regime of warm dense matter, where the atomic orbitals become partially ionized and they become more and more states become occupied as temperature increases, but they are not as ionized as a fully ionized plasma. So it's a very hard to describe state of matter. These conditions are relevant to study the interior of large exoplanets, as well as the conditions relevant to inertial confinement fusion. And one of the most common ways to access these states of matter is through the Hugoniot curve, which is basically the collection of thermodynamic states that are generated when you launch a shock into a material. And in this curve, we can actually observe some features that can tell us about the excitations of the different electronic shells. And this will be the main focus of this talk. So I will show you how we generate these equations of state and how we implement the linear mixing approximation and apply it to the three different materials I mentioned. And as a side note, all the equations of state for every material that I will mention in this talk is available in the literature that we have published. And it's also available in the link that I will provide at the end of the presentation, same as Burkhard provided. So the way in which our approach works is the following. We combine regular DFT molecular dynamics with path integral Monte Carlo. In path integral, the electrons are paths, and we integrate over all possible paths. And DFT considers the electrons as wave functions that obey a time-independent Schrodinger equation. So they are completely different approximations. They are different approaches, and we expect that they produce the same results at the same conditions. And to show you an example, I will show you the case of magnesium, which is one of our latest publications. And the way in which it works is the following. We basically perform a number of simulations at constant temperature and constant density. And for each of those, we extract the average energy and pressure. For the highest temperatures, we use path integral Monte Carlo. And for the temperatures that are roughly below 1 million Kelvin, we use density functional theory. If we monitor these properties that we obtain along an isochord, for example, as a function of temperature, we can see that both pressure and energy generated by DFT are consistent with those generated by path integral in this overlapping region. Therefore, we generate a consistent equation of state that spans across this wide range of temperatures that in this case goes from 20,000 Kelvin to almost 1 billion Kelvin. We have ways of monitoring how the electronic shells become ionized, and it's basically counting the number of electrons enclosed in a sphere of radius r. And you can see here how the magnesium ions become depleted of electrons as temperature increases. And this ionization decreases as the density is increased. Finally, we calculate the Hugonia curve with the energies and pressures we obtain. And that's how we obtain this figure I've been showing to you. And here we can recognize the excitation of L shell electrons in these peak at temperatures around 800,000 in the case of magnesium. And we don't see K shell ionization until we reach temperatures of 7 million Kelvin along the Hugonia. This, of course, occurs before radiation and relativistic effects take place. In the case of MgO and MgSiO3, you can see here that the Hugoniot curve we predict is in remarkable agreement with the available experiments that go even up to 3,000 GPa in the case of MgO. For the case of MgSiO3, there's also very good agreement up to 600 GPa and 20,000 Kelvin. So now that we have produced reliable equations of state that describe these materials, we proceed with the linear mixing approximation. And the idea behind this is the following. As I mentioned, we have generated equations of state of pure elements, pure magnesium, for example, pure silicon, pure oxygen. And we wonder, is it possible to combine these equations of state in a way that I can generate the equation of state of the mixture, the MgSiO3 mixture, for example? And the most simple way of doing this is through the linear mixing approximation, where at constant pressure and temperature, we predict that the volume of the mixture will be given just by this linear combination, same as the energy, which means that we're basically neglecting interactions. But since we have the original fully interacting equation of state of MgSiO3, we can compare it with this approximated equation of state and see where the non-ideal mixing effects take place. So for the case of MgO, we have here the equation of state of Mg and pure oxygen. Here's the Hugonia, where we can recognize the L shell and K shell ionization peaks. And when we combine them linearly, we obtain this golden dot dash line that you can see it overlaps the thick line in blue, which is the original Hugonia for the fully interacting MgO mixture. So what this means is that we are able to generate the equation of state of MgO just from linear mixing for a very wide range of pressures and temperatures. And we can see that this approximation breaks down in this case for temperatures below 100,000 Kelvin, which is for compressions below 3.2 fold. But you can see that the approximation is not as bad for the predicted pressure in the Hugonia, where we have much better agreement within linear mixing. Our curve also agrees very well with available experiments. In the case of MgSiO3, we see just a slight underestimation of the temperature, a even much better agreement with the pressure with the linear mixing approximation, which is this green line that overlaps again with the original fully interacting equation of state of MgSiO3. We can compress to a different initial compression density, and we again obtain very good agreement with the experiments, even with the extrapolation from linear mixture, which is this line over here. So for boron nitride, we can see that the Hugoniot curves of the elements are very different. Again, there's even a dissociation peak here. But when we combine them linearly, we obtain the Hugonia of boron nitride that is in the cyan line here, that again overlaps with the fully interacting boron nitride Hugoniot curve. And there's no underestimation of temperature, but rather a little bit of overestimation in this region here, but there's quite good agreement in general. So to finish, I just want to mention that the difference in densities, for example, within linear mixing with the actual density of the fully interacting material is very small. And we only have problems here in general when we paste the equation of state generated from PMC and DFT. But in general, the deviations are less than 2%. Same with the energies, that we also see them decrease on this difference with increasing temperature, and the deviations are in general smaller than 2%. So we have validated the linear mixing approximation and showed the linear mixing works for a wide range of pressures and temperatures. And I invite you again, as Burkhard did, to download our code that can generate new equations of state in this with this approximation. Thank you.
Thank you very much, Felipe, for this great presentation. So we have a couple of questions. The first one is, do you see core overlap in liquid phases from DFT calculations at high temperature, even much below 1 million Kelvin?
Yes, we actually do. And the good thing is that it's not really relevant. There's some core overlap because we have to choose a pseudopotential that is as good as we can get. We use a helium core pseudopotential for every species. So in that case, the 1s electron shell cannot be ionized. But for the highest densities, even those cores overlap, but that doesn't produce a big problem. It's just a problem with the calculations.
Okay, and the second question is, for the linear mixing, if you have different phases coexist, are the equation of states the same?
We have not tried that. We would have to compare with available data, but that's certainly something that we can do with our code here.
Okay, we still have time for one quick question if any speaker has a question. No? Okay, then thank you very much, Felipe, and we are going to go for the next talk, which is going to be given by Eric Galtier.